Welcome to the deep dive. We are going deep on algebra today. And I think this is going to be particularly interesting for you given your background in philosophy. We're not just talking about, high school algebra with X's and Y's, but really trying to get at the nature of algebra, what it is.
Yeah, we're looking at it as a fundamental branch of math.
Right, and really kind of getting into the way it informs even logic and reasoning. So we've got some great sources that we're looking at that give us a pretty comprehensive overview of algebra from, that basic high school stuff all the way to the abstract structures that are explored in modern mathematics. And I think what we really want to get at in this deep dive is, what is algebra? Not just how to manipulate equations, but like, what is it really about? And how is it that it can apply to so many different areas, domains? I mean, it's really domain independent in a way that's pretty remarkable. I think that's what really resonates with my philosophical interests, at least.
And that's what makes it so fascinating.
Yeah.
It's this idea of structure,
Right.
how things are put together,
Yeah.
and how we can reason about them,
Yeah.
even if we don't know what they are specifically.
So let's start with, elementary algebra, the kind of stuff that most people probably first encounter when they're, in high school. What are some of the core ideas there that we should keep in mind as we go deeper?
Well, I think the most important thing that elementary algebra introduces is the idea of a variable.
Yeah.
And this is really powerful. In arithmetic, when we say 3 plus 4 equals 7,
Yeah.
that's a definite statement about specific numbers. But algebra introduces variables like x and y and allows us to express general truths that hold for infinitely many cases. Like, for example, you take the commutative law of addition.
Right.
X plus y equals y plus x.
Yeah.
Now, this is one statement,
Right.
but it captures the fact that for any two numbers, the order in which you add them doesn't matter.
Yeah. It's a kind of a symbolic compression of infinitely many truths into one.
Exactly.
Yeah.
It's managing the infinite in a finite way. And that's a really powerful thing. And you see this all over in elementary algebra. Like, take the formula for the area of a circle, pi r squared.
Right.
That one formula allows you to calculate the area of any circle.
Infinitely many.
Yeah, for any radius r.
Huh.
And equations, they're not just about finding unknown values. They can also represent laws that are always true,
Right.
like the commutative law. Or they can represent constraints
Yeah.
that define specific solutions or relationships between different quantities, like the equation of a line, y equals 2x plus 3.
Right.
And that describes an infinite set of points,
Yeah.
but in a very concise way.
And of course, in elementary algebra, we're usually dealing with real numbers or complex numbers. But our sources make it pretty clear that algebra is not limited to these particular number systems.
Oh, absolutely. It goes way beyond that.
Right.
I mean, the basic principles apply to other kinds of numbers, integers, rational numbers, even modular arithmetic. But the really interesting thing is when you start to apply algebra to things that aren't numbers at all.
Right.
And that's where we get into abstract algebra.
Yeah, and that's where things start to get really, really interesting, especially from, a philosophical point of view where you're interested in the nature of structure.
Mm-hmm.
So what's the kind of fundamental shift that happens when we go from elementary algebra to abstract algebra?
Well, the big change is that in abstract algebra, we're dealing with algebraic structures,
Okay.
or just algebras for short.
Okay.
And these aren't limited in numbers. Like, you can take any set of objects. Let's say you have the collection of all subsets of a given set.
Okay.
Now, you can define operations on these subsets, like union and intersection.
Right.
Or you could take all the words that you can form from an alphabet,
Okay.
and you can combine them by concatenation,
Right.
just sticking them end to end, or by reversing them.
Okay.
Or you could even take the permutations of a set,
Yeah.
the ways you can rearrange the elements. And these permutations, you can combine them by composition.
Right.
And each permutation has an inverse
Yeah.
that undoes it. Now, each of these examples,
Yeah.
the subsets with union and intersection, the words with concatenation and reversal, the permutations with composition and inverse,
Right.
these are all algebraic structures.
Okay.
They each have their own set of elements
All right.
and their own specific operations.
Right.
And those operations obey certain laws.
Right. So it's really about identifying the underlying structures and how they work.
Exactly. And this is where the abstraction comes in.
Yeah.
Because we're not really concerned with the specific nature of the objects themselves.
Right.
We're interested in the rules that govern their behavior.
Right. And how they're organized.
Yeah. Now, the interesting thing is that even though the laws that govern these different structures might look similar, they can also have some subtle but important differences.
Right.
Like, for example, take the distributive law. In the algebra of integers, we know that multiplication distributes over addition.
Right. X times the quantity y plus z equals x times y plus x times z.
Yeah, exactly.
Yeah.
But now, if you look at the algebra of sets, there's an analogous distributive law. The intersection of a set, X, with the union of sets, Y and Z, is equal to the union of the intersection of X with Y and the intersection of X with Z.
Right.
So that's like saying, X intersect the quantity, Y union Z equals the quantity X intersect Y union the quantity X intersect Z.
Right. Okay.
But here's the thing. In set theory, you also have another distributive law.
Okay.
The union operation also distributes over intersection.
Okay.
So that means that X union, the quantity Y intersect Z, is equal to the quantity X union Y intersect the quantity
Right.
X union Z.
Right.
And that second law, that doesn't hold true for integers.
Right. So the rules aren't always exactly the same, even though they might seem similar on the surface?
Exactly. And this is one of the things that led to the development of abstract algebra. Because mathematicians started to realize that instead of just focusing on specific algebraic systems, like the real numbers, they could study classes of algebras that share certain fundamental properties.
Right.
And these properties are usually expressed as equations that the operations in those structures have to satisfy.
Right. Okay.
And this really took off in the 19th century. And it led to the systematic study of core algebraic structures like groups, rings, and fields.
Yeah, those are terms that we hear a lot in higher math. So can you maybe just give us like a simple sense of how those relate to each other?
Sure. You can think of it as a kind of hierarchy.
Okay.
You start with the idea of a group.
Okay.
And a group is basically a set of elements with a binary operation.
Okay.
That's an operation that takes two elements and combines them to produce a third.
Right.
And this operation has to satisfy four basic axioms.
Okay.
It has to be closed,
Okay.
which means that the result of the operation on any two elements is still in the set.
Right.
It has to be associative,
Okay.
which means that the grouping of the elements doesn't matter.
Okay.
There has to be an identity element,
Okay.
which is an element that doesn't change anything when you combine it with another element.
Right.
And every element has to have an inverse,
Okay.
which is an element that, when you combine it with the original element, gives you the identity element.
Right. So it's basically like you have an operation and a way to undo it.
Exactly.
Yeah.
And if the order in which you perform the operation doesn't matter, like if X combined with Y is the same as Y combined with X, then it's called an abelian group,
Right.
named after Niels Henrik Abel,
Okay.
a Norwegian mathematician.
Okay, so that's a group. So how do rings and fields fit into this?
So a ring is basically a group with an extra binary operation.
Okay.
That's kind of like multiplication.
Uh-huh.
And this second operation also has to satisfy certain axioms, particularly how it interacts with the first operation,
Right.
like the distributive law.
Right.
And then a field is a ring where every non-zero element has the multiplicative inverse.
Okay.
So you can do division.
Right.
Like if you think of a four-function calculator, addition, subtraction, multiplication, division,
Right.
that's basically reflecting the structure of the field of real numbers.
Right.
So it's like you're adding more and more structure
Yeah.
as you go from groups to rings to fields.
Okay, so abstract algebra is kind of moving away from focusing on numbers and more on defining things in terms of the properties of these operations.
That's right. Like the abstract definition of a group doesn't say anything about numbers. It just talks about a set with a binary operation that satisfies certain equations.
Okay.
And this is where it gets really mind-blowing.
Yeah.
Because that binary operation doesn't even have to be commutative,
Right.
which means that X combined with Y doesn't have to be the same as Y combined with X.
Right. So that's different from, addition and multiplication of numbers where it doesn't matter what order you do them in.
Exactly. And that's where we get non-abelian groups,
Okay.
where the order of operations really matters.
Okay, can you give us an example of that?
Sure. A classic example is the permutation group S3,
Okay.
which consists of the 6 possible ways to rearrange 3 objects,
Okay.
like the letters in the word Dan.
Okay.
So if you swap the first 2 letters,
Okay. Yeah.
you get an,
Okay.
and then you swap the last 2 letters,
Okay.
you get an.
Right. Yeah.
But if you do it in the opposite order, you get a different result.
Right.
So first, you swap the last 2 letters, you get DNA,
Yeah.
and then you swap the first 2 letters, you get an.
Right.
So the order matters.
Okay, so the order of the operation actually changes the outcome.
Yes.
Okay.
And another example of a non-abelian group is the operations on a Rubik's Cube.
Right.
The order in which you turn the faces matters a lot.
Yeah.
And rotations of a sphere in 3 dimensions, that's also a non-abelian group.
Okay.
It's denoted as SO3.
Okay.
But rotations of a circle, that's an abelian group. Because the order in which you rotate doesn't change the final orientation.
Right.
So SO2, the group of rotations of a circle, is abelian.
Right, so you've got these different structures, and in some of them, order matters, and in some of them, it doesn't.
Exactly. And that's just the beginning.
Yeah.
There's a whole universe of algebraic structures out there,
Right.
each with its own unique properties and applications.
So, like, what are some other ones?
Well, there are vector spaces and modules,
Okay.
which extend the ideas of rings and groups to deal with how one set of things, called scalars, can act on another set of things, called vectors.
Okay.
And that generalizes ideas from linear algebra.
Right.
Then there are monoids,
Okay.
which are like groups, but you don't need an inverse for every element.
Okay.
Like the natural numbers under addition form a monoid
Okay.
because there are no negative numbers.
Right.
But they don't form a group
Okay.
because there's no way to undo addition.
Right.
There are no inverses. And then there are Boolean algebras,
Okay.
which are an algebraic framework for logic and set theory.
Right.
So you have operations like and, or, and not.
Right.
And then there are lattices,
Okay.
which are like Boolean algebras, but they're even more general.
Okay.
They're abstract models for order relations.
Right.
So you can see that algebra pops up all over mathematics.
Yeah, it's really kind of a foundational way of looking at things.
Exactly. Because its focus on structure, it's become an essential tool in lots of different branches of math.
Likely.
Well, you've got algebraic logic, which uses algebraic methods to study logical systems.
Okay.
Algebraic number theory, which uses algebraic structures to study numbers.
Okay.
Algebraic topology, which uses algebra to classify topological spaces.
Okay.
And then there are whole fields like algebraic geometry and algebraic combinatorics, which are huge areas of research in their own right.
Right.
So algebra's influence is really pervasive.
Okay, so now let's talk a little bit about the philosophical implications of all this. What are some of the things that might be particularly interesting to someone who's, thinking about big philosophical questions, like the nature of reality and reasoning?
Well, I think one of the most profound things about algebra is that it's domain independent.
Okay.
A lot of other branches of math are tied to specific kinds of objects. Like geometry is about space,
Right.
and analysis is about change.
Right.
But algebra, it doesn't really care what the objects are.
Right.
It just cares about how they're related to each other.
Right.
And that makes it very similar to formal logic,
Right.
which is also trying to find general principles of reasoning that apply to any subject matter.
Right. So it's like there's this kind of underlying connection between algebra and logic.
Exactly. And that suggests that there might be some deep unity between different areas of thought.
Right.
Our source even talks about a kind of duality between elementary algebra and abstract algebra.
Yeah, I saw that.
They compare it to Cartesian dualism.
Yeah, that's a really interesting analogy.
Right. So the idea is that elementary algebra, with its focus on manipulating symbols and solving equations, that's kind of like the process of mathematical reasoning.
Okay.
It's like the mind of mathematics.
Right.
Whereas abstract algebra, which focuses on the underlying structures themselves, that's more like the body of mathematics.
Right. The objects themselves?
Yeah.
Okay.
So you have this kind of interplay between the act of reasoning and the structures that we reason about.
Yeah, that's really fascinating. And I think, as we've been talking about, the connection between algebra and logic is particularly relevant for philosophical questions about the nature of truth and inference.
Absolutely. Algebra has played a huge role in clarifying logical notions. Like the transition from Aristotelian syllogisms, which were based on the structure of language, to a more symbolic and algebraic approach to logic. Yeah.
That
That really started with George Boole in the mid-19th century. He showed how logical propositions and inferences could be represented and manipulated using algebraic equations.
Right.
And that created Boolean algebra,
Right.
and that provided a much more rigorous foundation for the study of reasoning.
Okay.
And this led to a big division in the field of logic between the formalistic approach, people like Frege, Peano, and Russell,
Right.
and the algebraic approach, people
Mm.
like Peirce, Schroeder, and Tarski.
Right.
And you could say that this division kind of reflects the dichotomy between elementary algebra and abstract algebra.
Yeah, it's like the same kind of distinction is playing out in both fields.
Right.
So algebra is not just about numbers.
No, it's much deeper than that.
It's really about this kind of fundamental way of understanding structure.
Exactly.
And it applies to all sorts of different domains.
Yes, from mathematics to logic and beyond.
And I think what's really powerful is that by abstracting away from specific examples, Algebra allows us to see the common principles that govern these different domains.
That's the beauty of abstraction. It allows us to see the forest for the trees,
Yeah.
to identify the underlying structures that connect seemingly disparate things.
And that's a really powerful insight, I think, for anyone who's interested in understanding the world.
I agree. It makes you realize that there's a lot more order and structure in the universe than we might initially think,
Right.
and that there are powerful tools like algebra that can help us to understand that structure.
So to kind of bring it all back to our listener who's, got this philosophical mind, what are some of the kind of final takeaways here?
Well, I think the main takeaway is that algebra is not just about manipulating equations.
Right.
It's a profound way of thinking about structure and relationships,
Right.
and it has deep connections to logic and reasoning.
Right.
And it can be applied to an incredibly wide range of domains.
Yeah.
So as you continue your own philosophical explorations, think about the implications of algebra's abstract nature.
Right. What does it mean that the same set of laws can govern such different kinds of objects?
Yeah, and how does the algebraic approach to logic inform our understanding of the very process of reasoning?
Right. And maybe you want to even look into related areas like category theory, which takes the ideas of algebra to an even higher level of abstraction.
And maybe the most profound question to ask is, could the structures and principles that we find in abstract algebra provide a universal language for describing not just mathematics, but all forms of structured thought?
Right. And maybe even reality itself.
Exactly.
That's a pretty big question to think about.
Yeah, but it's one that algebra can help us to grapple with.
Well, thank you so much for taking us on this deep dive into algebra.
It's been my pleasure.
And for you, our listener, keep thinking about those big questions. And join us next time for another deep dive into the ideas that shape our world.